Next, we have Christopher Higgins. He is the Cecil and Sally Drinkward Professor of Structural Engineering at Oregon State University.
It's nice to be here this morning to talk to you about a material that is not widely used for civil engineering structures, and that's titanium. I want to recognize my graduate students who really do all the heavy lifting in terms of taking this material from concept all the way into specifications. So overview, I'll talk about the introduction, background, and motivation for this work, as well as the full-scale laboratory tests that are the basis for the design recommendations. Talk about the first field application of this bridge in Oregon on a bridge over I-84. I'll talk about a brand new AASHTO guide specification, as well as a new ASTM material specification and some conclusions. We've got a whole bunch of older bridges that were, particularly in reinforced concrete and pre-stressed concrete, that were designed during kind of a boom of the post-war. And during this period of time, designers had a brand new material they could use, and those were deformed reinforcing bars. And they're the same deformed reinforcing bars that we use today. But in 1950, they were brand new, and they had these standardized deformations. Prior to that, you had no idea what kind of bars were going to show up on your work site, so you had really good detailing. You'd had all kinds of bends and anchorages to make sure those bars were going to be able to be developed. But when we now have these beautiful deformations, we could terminate them with straight bars. We can get rid of all those bends. At least we thought we could. At the same time, we were overcounting what the concrete could do, particularly for what its shear contribution was. And so as a result, we were putting more concrete in, less steel, and the steel we were putting in wasn't well detailed. And as a result, we've got some problems and deficiencies in those bridges, things like cracking and diagonal tension cracking in particular. And now we go to evaluate them with modern design codes, and we find they just don't pencil out. All right, so we've got some choices here. We can either replace them, we can limit loads, we can retrofit them. All right, and at least in Oregon, to post a bridge is politically, it's poison. We don't have the money to replace them, so retrofit becomes our primary alternative. And of course, there's lots of different approaches one can use, carbon fiber being the most likely material for people to look at. One of the difficulties with FRPs is that, particularly with pre-cured laminates, right, you can't bend them. And then we're relying only on, almost exclusively on bond behavior to get them. So even though they're high performance, they're non-ductile. And we don't use metallics because we're concerned about some of the corrosion issues with most metallics. So here's some carbon fiber for you. It's hard to see maybe some of the numbers there, but the elongation at fracture is about 2%, right? So that's not very much, even though it's very high strength. This is if you're just testing the carbon bar, not the system. And so you can't really actually get full use of that material at 325 KSI because you're going to fail the bond. And this is a picture of a wet layup. We've done a lot of work with carbon fiber as well. And you can see this is a screenshot at the point of failure, and you can see kind of those yellow arrows are pointing to the point where you're essentially ripping off the carbon fiber from the surface. These wet layups really are bonding to the worst part of your concrete, which is the skin, right, that's subjected to all kinds of freeze-thaw exposure. It's mostly made up of paste, even though you do some surface grinding. So the alternative then for that is what's called near-surface mounting, and that's where you cut grooves in the concrete so you can get a little bit more anchorage in the body of the concrete, but you're still in the cover. And in those grooves, then, you're using a structural epoxy to bond in a type of bar, and carbon fiber is, again, the most common type. And we've done work with this with carbon fiber, and you find that if you have widely spaced carbon fiber, you end up with, so you can see this is a pre-cured bar that's kind of ripped out of the groove of the epoxy groove. So the bar's still intact, but we've failed the bond. If we have really tight bar spacing, essentially what we do is we rip off the cover. It does a great job of reinforcing the cover, but underneath this, there's a huge diagonal crack, right? So we've actually kind of dismembered the parts, right? So the core of the concrete is disconnected from the outer surface. What's out there, right? So when we look at the problems we were getting with some of the behavior with carbon fiber, we're looking for alternatives. And really what we want is something that's environmentally insensitive material with high strength but well-defined material properties. We'd like it to have ductility. And we'd like to have something that has inherent anchorage built into it. So we're not just relying on the bond along the length, but we can actually anchor the ends of them. And that's what leads us to titanium alloy bars. And really you can think of it as ductile FRP. Titanium, well, that's crazy, right? Nobody uses titanium in civil engineering. It's simply too expensive, right? If you just value things on price per pound, yes, it's an expensive material. But you'll see that it doesn't only win in the air when you care about lightweight, right? And if you care about a medical device like a brand new knee or brand new shoulder, right, that's likely to be titanium. So it's not just for those. And hopefully you'll see it by the end of the presentation that it's not just about price per pound. So here's a typical stress strain plot for the titanium alloy bars that we're using. You can see it's elastic until we reach yield. We don't have a well-defined yield point, so we're using a 0.2% offset to define yield. But yield for this material is in the neighborhood of 140 KSI, the real yield strength. The specified yield strength is 130 KSI. You can see that the elongation out here is about 11% elongation, more than 11% elongation. So it's high strength, but with ductility. Young's modulus is about half that of steel, a little more than half. And in general, pretty good behavior. So here's kind of an overview of the material properties. We're using not pure titanium. We're actually using an alloy. This is the same material that's being used by, in fact, it's typically going into aircraft fasteners at Boeing or Airbus. It's got 6% aluminum, 4% vanadium, and that's the spice that makes it work. It has well-defined high strength, and it's ductile. Right? We can limit the strain hardening effects, and you can think of it as kind of an ideal structural fuse. So if you're looking to force protect elements, it's a great material. It has high fatigue resistance with a constant amplitude fatigue limit of about 75 KSI. It has low notch sensitivity, right? So we're not worried about fatigue of the titanium, we're more worried about fatigue of your reinforcing steel. Impervious to chlorides because it forms a very stable oxide layer almost immediately, and that's why we use it in joints. We're very salty creatures, and we don't worry about corrosion of your hip or your knee. Its coefficient of thermal expansion is about 8.6 microstrain per degree C. If you think about concrete, it's in the neighborhood of 8 to 12, and steel is 12, right? So it's actually very compatible with concrete. It's almost made to go together. We're not going to generate thermal stresses due to incompatibility. We can use conventional fabrication techniques, meaning we can shear it, we can cut it, we can bend it, we can actually torch it. It's relatively lightweight, about steel, it's about 1.7 times less. And we can bend it, right, because it's a metallic, and therefore we can integrate an anchorage at the end of the bar, so we're not just relying on bond. All right, so we like to break things, and we like to break things at full scale. So everything we do is tailored to produce old beams with new materials that think they're old beams, right? So these are beams that think they're in the 1950s. We've got a kind of a malt shop in our laboratory to make them feel at home with poodle skirts. We've got 10 different shear specimens, 10 different flexural specimens, and we have 3 specimens that are kind of unique where we are subjecting them to high cycle fatigue at the same time that we're subjecting them to freeze-thaw exposure, because we're interested not just in this immediate performance, but also long-term durability of what we're doing. Our typical specimens weigh about 20,000 pounds, right? They're 4 foot high, which is a typical size for these girders, and about 24 foot long. We've used a number of different epoxies over time because epoxies change. Bond strength is probably the most useful characteristic. And you can see our bond strength, the one with the highest bond strength is actually the worst epoxy. For shear strengthening, we're actually producing stirrups. All right, so we have a continuous stirrup and we have single leg stirrups depending on, let's say if you've got a box girder, you might want a single leg stirrup. If you've got a deck girder, you might want a continuous stirrup. The advantage of that continuous stirrup is you get confinement and you get to anchor these hooks inside the core. So this red highlight is our titanium stirrup. Essentially, we're cutting the groove in the concrete all the way around, and then we're hammer drilling a hole for that hook. And we fill that with epoxy, we bond in a stirrup. So you get good anchorage at both ends of the hook. Right? So I can develop the actual strength of that titanium bar. Here's some installation. This is really just a fancy skill saw that's wired to be wet. We like to duct tape the sides so it gives a nice clean appearance. We're putting epoxy in and we put the bars in. We test them. This is a picture inside our large environmental chamber. This is a hydraulic actuator that's through the roof. We're bouncing it up and down. Based on field measurements of real bridges, the stress ranges that we're producing are amplified so that we can accelerate the service life, and we're using Miner's rule essentially to come up with an equivalent stress range. And for producing 13 KSI stress range in the stirrups, we can do about 2.4 million cycles, and we can make the argument that represents about 50 years of service life. At the same time it's bouncing up and down, we're also freezing and thawing it. And in Oregon, we have a pretty broad range of environmental conditions. And so we've got 120 freeze-thaw cycles happening simultaneously with those fatigue cycles. And we can say that those 120 cycles represent anywhere between 25 and 100 years of service life, depending on where in our state you are. So here's a picture of a failed girder in diagonal tension, or shear if you prefer. And this is a close-up view. And if you can see up close, this is another one. There's the fractured titanium stirrup. We're actually making full use of that material. We're not throwing it away. All right, that's the beauty of those hooks and bends. Here's the load deformation response. A control specimen shown in green. The red specimen is if we just put it on the lab floor and test it, we can get an additional, almost 100 kips out of this thing. That's per girder, right? Typical bridges are 4 girder lines, so you can see you can get significant strength increases. The blue line here is our fatigue and freeze thaw, and then we put it on the strong floor to test it to failure. And you can see we get the same behavior and the same strength out, even if we bounce it up and down before we test it to failure. So we see no environmental durability problems. For flexure, typical problem we're trying to fix here is we've got diagonal cracks in our girders, and then these are terminating around a cutoff location. And so what we're using these titanium bars essentially to act as non-contact lap splices to extend that bar closer to the support so that we can bridge over that deficiency. This is an inverted T. This is one where you'd have a negative moment region. And here we're putting our titanium bars in the soffit of the deck because most of our work we like to do under open traffic. And so we don't like to have deck work done on top. We can work from underneath. We're throwing away some inefficiency in terms of where the depth is, but in terms of actual practical applicability, making them work. We make this really hard on the girders, right? To simulate those diagonal cracks, we cast inside the girder when we make these things a polycarbonate sheet, right? So we take away all that aggregate interlock, or what people believe is aggregate interlock as a shear transfer mechanism, and we make either our stirrups and the flexural steel crank up high demand in those because of that. So here's a picture of the construction. We've cut the grooves here, essentially 3 saw cuts, passes, and then with a chisel you kind of just chip them out. And then at the end of each one of those grooves we hammer drill a hole that's going to anchor in our hook. We're using ACI 440, which is the FRP specification in terms of groove spacing and the groove dimensions. Here's how we do our hooks. It's a smart material, meaning it comes to us silver, and to bend it we have to warm work it. It's actually like high strength rebar where you have to warm work it as well. We started out thinking we need something fancy, so we got a nice kind of induction oven here to cook it, but then we realized that we just use an oxyacetylene torch. It turns color when you heat it, and so the temperature we need is in the neighborhood of 900 degrees to 1200 degrees Fahrenheit to bend it. You say, wow, that's hard to get. Not really. It tells you it turns yellow when it's at 900, and it's kind of that yellow here. We like to call it straw. It's a fancier word for yellow. And when it turns 1200, it's a blue color, a nice kind of gunning blue. So it will tell you when to bend it. And then we just bend it in our conventional rebar bender. Here's a controlled specimen, all right, and what we've done there, the bar cutoff, the flexural bar cutoff is here, and this, essentially that bar, all these cracks that you see is that bar inside slipping, which leads to failure. So it's a kind of a tension anchor failure. And this is the same girder. You can see the titanium here added on the sides. Same cutoff location. In fact, we made it harder. We made the development length 1/3 instead of a half to even make the titanium work better. And in fact, we fail it in flexure where the titanium bars end, but those steel bars are well anchored, and that's really what your intent is with a repair, is to take away the defect and force the failure into a ductile location. So the control specimen is shown in blue. We reach a peak load, and essentially it would have failed if it's a load control. Once we add the titanium, essentially we can increase the strength, and it continues to gain strength even after the steel anchorage has failed because the titanium is doing all the work, and we get very large deformation. So that large deformation essentially gives you a good sense of warning. Here's a picture again. This is a control specimen. Fails because of the tension anchor. This is a negative moment region. Rather than push up, we just roll the girders. So we're producing a negative moment with high shear. And again, we put in our titanium bars in the soffit of the deck, and we move the failure mode into a ductile failure mode at the end of the bars. Again, control in blue. With the titanium, we get that nice ductile behavior. Again, we do the same thing in terms of our freeze thaw and fatigue. And then we test them. Control specimen shown in black. Red is if I just test it without the durability. Blue is including the high cycle fatigue and freeze thaw. And again, we get almost the exact same answer, even though we did a heck of a lot more work with the fatigue and the freeze thaw. So no environmental deterioration. Here's our first application of it. We now have 9 bridges in Oregon that have been retrofitted with titanium. This is the first one over I-84. This is built in 1952. Bridge inspectors go out, they see large cracks with vertical offsets. We ran some numbers and we said, kind of bridge wants to collapse onto I-84, you might want to close it. They did, they put up emergency shoring. Interesting thing, it's served by 2 quarries, one of which is ODOT's. Short base, heavy trucks. So this is kind of an overlay of the cracks shown in red with the reinforcing details. And right at this location where the girder kind of goes from prismatic rectangular to haunching, and it also tapers. It gets wider as well as it gets deeper. This is for dead load. This is actually in compression. And so there's no reason for this to have these kind of bars being spliced. There was no stress. And even if the live loads for the 1950s, there's not a lot of tension. But when you look at the trucks that were actually running over these things, they're producing high tension in this splice region. That's really our defect that we have to kind of fix. We built 3 replicate specimens, 1 to look at what would the behavior be if we did nothing. And then 2, we actually said, let's fail the girder, because that's what the designer thinks has happened, is the girder is failed in place, so it has no reserve capacity at all, and we have to get the repair to do everything. And then the third one is, well, there's probably some strength there, so let's not fail the girder. We'll just build a girder, add the repair, and let's see what happens. And we really cherry-picked mill certs to make sure we could match the bars to what the actual capacity was. It's kind of a funky girder, you know, it's got all kinds of geometric problems and changes. So we tried to build the best replica we could at full scale. This is a control specimen. Essentially, it's a very fast test. Because there's a negative moment for dead load, we actually produce the negative moment here when we do the repair, and then we apply the live load, which goes positive. So we're trying to actually simulate the real stress conditions as well. So this is start of the test, a little bit of cracking, done. All right, it's pretty quick. And in fact, if you look at the cracks that are produced, they're very much like the cracks that are observed in the field. Here's the load deformation response. Very poor performance. This is what we believe. The orange line here is what if you do your calculation, what we think the demand should be. There's very little reserve strength. All right, so here's the boring stuff. Here's the load deformation response. So the red's the control. Remember, I had one that I failed first and then repaired? That's the green one. That's the highest strength. The blue one is the one that I didn't fail first, and then I applied the titanium, and it actually gets lower strength. And you might say, wow, so if you fail it first and add the titanium, you get the best performance. And the answer is yes. And the reason for that is the titanium is what controls the strength. But that steel wants to participate. It's like the little dog that chases the big dog, right? That steel tries to work, and then it fails. And then it creates damage around because it slips, right? And that damage actually affects some of the bond that's attached to your titanium. And so that's why you get kind of this reduced performance if you have the steel and titanium participating. If you just get rid of the steel and just have titanium, you get the best performance. And we actually have done some work for seismic retrofits where we have purposefully cut the steel to just allow the titanium to do everything. And again, we get the best performance if we just let the titanium do it. Those lines on there just tell you that, hey, we can predict the behavior. It's easy. All right, so here's the finished repair. We had, because it was the first application, they actually had a carbon fiber retrofit, and the bids came in, and actually, even though nobody had ever used titanium before, it was 30% cheaper than the carbon fiber. How do you use this? Well, there's a brand new ASTM specification, comes out of Committee B10, which is the reactive and refractory metals and alloys, or aka titanium. It was approved last November. So you now have a brand new standard specification for titanium alloy bars for civil infrastructure. Essentially, it tells you all the properties you'd need, just like it were rebar. And how do you design it? Well, we have a brand new AASHTO approved design guide, which was just passed in Alabama this past summer. Essentially, it walks you through the design using the AASHTO LRFD format, or lays out the general conditions, the materials. It references that ASTM specification. It tells you how to do the construction, how to do the installation, and how to do the design for both shear and flexure. And for flexure, we include modified compression field theory, just like you're used to doing in LRFD for conventional steel and concrete. We're using conventional analysis methods, right? So line girder analysis, distribution factors, all those things. In fact, we tell you to do that because you don't want to do a refined analysis. You want to do an old-fashioned analysis because it's conservative. We want to design those titanium bars to be at yield if you meet the conditions. It also includes an environmental durability factor because you don't know what epoxy people want to use. If you use good epoxy, then you don't have to worry about durability. The titanium is not going to go anywhere. I always like to say at the end of the world, when the cockroaches are dancing in the kind of the radiation, they'll be dancing on top of the gleaming titanium bars. Right? Everything else will be turned to dust. We have 3 limit states. So we have strength, we have service, and we have fatigue. Now, fatigue is one that you don't worry about the titanium. You're just checking your steel to make, because if your titanium is fatiguing, your steel is not there anymore. And finally, there's a comprehensive design example for both shear and flexure. All right, so in conclusion, what we've kind of come up with is titanium alloy bars. We call them TIABs. They have these very lovely, well-defined material properties that have high strength and ductility. They're environmentally durable, and we can fabricate mechanical anchorages, so we can actually make use of that high-strength material, and we can do it easily. It's cost-effective. On the latest project that OJUT just did on a post-tension box girder to shear strengthen it, it was the maintenance crews themselves did the work. It was a $200,000 project. The cost of the titanium was $17,000. But guess what? The epoxy is $19,000. That's what I tell everybody. You know, the epoxy is actually the expensive part. The titanium's cheap. And once you decide you need to do something, it doesn't matter what material you're going to use. The cost of the material is not it's not driving the problem. So to really value something on a cost per pound basis makes really very little sense. We already said there are 9 bridges in Oregon that have been retrofitted, both for flexure and shear, and we're doing more of them. And I think across the country there's a number of DOTs that are, I think Texas has one in the works right now. So we believe all these attributes make this titanium alloy bar a promising material to economically strengthen bridges as well as other structures. With that, I'd like to acknowledge the Oregon Department of Transportation, Bruce Johnson, who was he's now our former chief bridge engineer, who is really a forward thinker and lets us do some interesting things. Our technical advisory committees and research group as well. It's Perryman Company, who actually is the material supplier. It's a U.S. product, by the way, so Buy American, as well as a number of undergraduate students that help us in the lab.
When you use the titanium and you're increasing the crack size, how are you dealing with the environmental factors regarding cracking of the existing steel?
You're actually, by adding the titanium, reducing the cracks, right? So you're adding reinforcing, and that gives you less cracking at service level. At ultimate strength, you're going to have big cracks. In fact, the big cracks are good because your inspectors will be able to see it before it fails. But at service level, that's why we have a limit check on the service limit to check bond, so that you don't get big cracks at service limit states. All right, thank you.
Thanks, Chris.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.